The term pharmacokinetics is derived from the ancient Greek words pharmakon and kinetikos, meaning drug and putting in motion respectively. It studies the way that the body reacts to and affects a pharmaceutical substance in the body. The four main components of pharmacokinetics are liberation, absorption, distribution, metabolism, and excretion. This process is known as LADME, and it describes the route of the drug since it enters the body until its excretion. Liberation is the first step. It is the process in which an active principle is released from the pharmaceutical form that contains it. The liberation process begins when the pharmaceutical form comes into contact with physiological fluids. This initial wetting leads to disintegration, which is the breakdown of the solid pharmaceutical form into small granules. As a result, the surface area increases, facilitating the dissolution process. Then, these disintegrated granules are diffused in the medium, disaggregation. And finally, it arrives as fine particles at the absorption site, diffusion. According to the therapeutic aim and the physicochemical properties of each drug, solid pharmaceutical forms can be formulated as either conventional or modified-release tablets. Immediate-release tablets are designed to disintegrate and dissolve completely upon exposure to physiological fluids within a short time, 2.5 to 10 minutes. This release form is employed in formulations that require a rapid onset of action or to improve the bioavailability of poorly soluble drug substances. On the other hand, modified-release tablets can be retarded release, where the liberation occurs in the small intestine passing through the stomach and its acid pH without degradation thanks to its enteric cover, is used in active principles that are degraded in the stomach and need to be protected. And controlled release, where the liberation occurs gradually over time, prolonging the therapeutic effect. It can be sustained release, where the active principle is liberated at a constant speed, maintaining constant plasmatic concentration. And extended release, where the active principle is liberated in different pulses. This release form is helpful to reduce the administration frequency, improving adherence. The next step of the LADME process is absorption. It is the process in which a pharmaceutical substance enters the blood circulation in the body through the diffusion across biological membrane barriers that are composed by cell layers that control the entrance of substances into the body. The key composition of the barriers is the lipid bilayer of the cell membrane, which is semi-permeable and modulates cellular transport by the following mechanisms. Simple diffusion is the no-energy-needed transport where the molecules move from an area of greater concentration to an area of lesser concentration. The diffusion speed depends on the size, lipophilicity, and ionization grade of the molecule. Facilitated diffusion, where a transporter canal protein makes a complex with the substance, diffusing it through the cell membrane without energy waste. The substances must be chemically compatible with the transporter protein. Active transport, where the substance enters the body against the concentration gradient with the help of transport proteins with energy expenditure. The fraction of a drug that is absorbed into the systemic circulation is referred to as its bioavailability. There are different absorption sites depending on the administration routes of the pharmaceutical forms. For example, oral dosage forms are absorbed through the gastrointestinal tract membranes. On the other hand, topical dosage forms as intradermal and subcutaneous medicinal products pass through the skin, and parenteral dosage forms pass through a tissue layer to reach the circulation. Intramuscular dosage forms pass through the muscle layer, while intravenous dosage forms don't have absorption, as the medicinal product is delivered directly to the bloodstream. Distribution. It is the transportation process in which a pharmaceutical substance is dispersed through the fluids and tissues to reach its site of action. This transport depends on the physicochemical properties of substances in general. Drugs are transported in solution as free, unbound, drugs and partly reversibly bound to transport proteins. Albumin protein binds to acidic drugs. Globulin binds to basic drugs. Lipoproteins transport big lipophilic molecules. The equilibrium between unbound and bound drug fractions is determinate because only unbound drugs are available to cross cellular membranes to reach the drug receptor. The distribution process occurs considering two hypothetical compartments that divide the body according to the blood irrigation of the organs. The central compartment includes the most perfused organs: heart, brain, lungs, kidneys, gastrointestinal tract, and liver, where the distribution of the drug is immediately. On the other hand, the peripheral compartment includes less perfused organs such as muscle and fat tissue. The distribution of the drug between those mentioned compartments depends on the hydrophilicity or lipophilicity of the active principle as well as the place of the target site of action. It is the process in which the drug is transformed into metabolites to excrete them. The liver is the principal organ responsible for this process, as is the organ designated to exogenous metabolism. Although the goal is to eliminate strange substances from the body, some produced metabolites are active and can have a pharmaceutical action. And an inactive or weak substance that has an active metabolite is added to the pharmaceutical form as a prodrug. The aim of metabolism is to convert nonpolar molecules to water-soluble metabolites to make the excretion process easier. The metabolism has two-phase reactions. Phase 1 reactions are the modification of the substance by oxidation, reduction, or hydrolysis. Phase 2 reactions are the conjugation of the modified substance with an endogenous substance, e.g., glucuronic acid, sulfate, glycine. The enzymes involved in the hepatic metabolism are mainly the isoenzyme family of cytochrome P450. They can be induced or inhibited by other substrates altering the drug metabolism. Excretion is the process in which a pharmaceutical substance is removed from the body. This process can be through biliary, intestinal, pulmonary, dermal, mucous, or renal routes depending on the substance's polarity and size. The kidneys are the principal excretion organs. In these highly perfused organs occurs the renal filtration, where the plasma that reaches the glomerulus is filtered. Nearly all water and most electrolytes are passively and actively reabsorbed from the renal tubules back into the circulation. However, polar compounds, which account for most drug metabolites, cannot diffuse back into circulation and are excreted. Other drug metabolites are excreted in the bile, reaching the intestine for further elimination. The high molecular weight substances bigger than 300 grams per mole, and the most nonpolar ones are most likely to be excreted by this route. Phase 2 reactions, mainly the conjugation with glucuronic acid, facilitate biliary excretion. We have talked about how a drug moves in the body. This is called the LADME process. Each step is important. Thank you for watching. See you in the next video, where we'll keep learning how to bring pharmacology to life, one concept at a time.